And hello and welcome back to the second part. Let's hope that the stream will hold now. Oh, didn't start yet. Hello and welcome back to the second part of the stream. I think it's working. The problem is limit x goes to infinity 1 plus 1 over x to the x, and we said that this is one of those problems where you have 1 to infinity, which is the first case, and we apply ln to both sides, and we use a formula for logs which will take off the power and put it in front of the ln, giving us infinity times 0 situation. Once we have infinity times 0 situation, we can use our 1 over f and get ln y is equal to limit x goes to infinity of ln 1 plus 1 over x divided by 1 over x, which is 0 over 0. So we can use L'Hopital rule now. So ln y and the L'Hopital is going to be limit x goes to infinity. Two separate derivatives. One on the bottom is easy. Now one on the top is the function itself in denominator and derivative of it in the numerator. And depending on how good your algebra is, if you do this, I'm going to say A, B, C, and D. You can clearly see that A and C, one is numerator, one is denominator, right? Once they multiply, so they actually cancel. There are other ways in which you can solve this, but whatever you come up with, ln y is equal to the limit x goes to infinity, and now you have 1 over 1 plus, come on, plus, there we go, 1 plus 1 over x. And now, when you plug infinity, you see that you get 1. From where ln y is equal to 1, we e both sides, and we get that y is equal to e. But remember that y was the limit, so what we found is the limit x goes to infinity of 1 plus 1 over x to the x is equal to e. This is your definition for e. And this is why I said at the beginning of this problem, it will be embarrassing when you're in Calc 2 or differential equations that you don't know this. One of the most important numbers that drives much of our science of physics and so on.
Now?
Yes. I hope. Let's see. Yes, working. So that was the first problem. And now let's take a look at another problem. The one that I mentioned before. It was sine on tangent. Let's say 58. We have limit theta goes to 0 plus, so from the right, and we have sine theta raised to the tangent theta. So this would be 0 to the 0 case. So the way to solve this is again to say y equals, leave some space for ln, limit theta goes to 0 plus of sine theta raised to the tangent theta, and you apply ln to both sides. It should be clear that ln is the correct choice because you have the exponent that you have to get rid of, and the logs are the only way to do that. Yes? So ln y is equal to, remember that we kick limit out all the way, and then we take the exponent down, and then we have ln of sine theta, multiplication there. Tangent of 0 is 0, and sine of 0 is 0, ln of 0 is infinity. Positive, negative, infinity doesn't matter. So we have 0 times infinity, in which case we use the 1 over f trick. So ln y is equal to the limit theta goes to 0 plus, and then we can say ln sine theta divided by 1 over tangent theta. So now you have infinity over infinity case, which means that you can apply L'Hopital's rule because you have indeterminate form. So ln y by L'Hopital now, we have the equivalent problem, limit theta goes to 0 plus, we take derivatives. Sine theta goes denominator, derivative of sine is cosine theta, goes in the numerator, and on the bottom here, what's 1 over tangent theta? Yes, it's a cotangent theta. So what's the derivative of cotangent theta? Very good. No, that was really good. Yes, that's correct. Negative cosecant squared theta. Great. So now, what I'm going to do here is do algebra rather than try and compute. I'm going to leave cosine theta over sine theta because I'm going to write this one as negative 1 over sine squared theta. And I am going to try and simplify this. So I will have negative cosine theta sine squared theta divided by sine theta. So remember, two that are far apart multiply and two that are close by multiply. So eventually I have ln y is equal to limit theta goes to 0 plus, and now I have one of these signs cancel, and we have negative sine theta cosine theta, which is equal to 0. So ln y is equal to 0, e both sides, from where y is equal to 1, and we got e again. Now it's not every problem is e, it's not. This one happened to be. So limit of sine theta raised to the tangent theta is equal to e.
Can you explain that last step? Just the e-ing both sides.
E and ln are inverses of each other. You can solve that in two different ways. So there is a formula in Precalculus which says a raised to the log base a of x is equal to x when bases are the same. In this case, we know that the log base e of x is written as ln x, so that's a faster version. So e to ln x is just x. So if I e both sides, these guys cancel, leaving just y behind, and then e to the 0 is 1.
Oh, so you're okay. I thought you're multiplying. Well, I was confused.
I'm applying e.
Yeah.
Okay? Good. Do you want another one? Just in case, because you love this one so much? Yeah? Yeah, all right. The whole classroom lit up. Everyone raised their hands. Too bad you can't see all of this. It's the happiness and joy of the Saturday morning class. Calculus for hours. Yes, that's ln x in the exponent. Enjoy. Yeah, previous problem is 1, but the e to the 0 is 1. I wrote e to the 0 is e. Previous problem is 1. Just fix that, because e to the 0, when you e both sides, I said y is equal to 1. And I don't know why I wrote e over here. It's 1. The answer is 1. Wow. Let's just cover that up like this and move on like nothing happened. Just wanted to see. Yeah, correct so far. Everything is 100% correct. I was laughing on the next step. No, I was laughing on the next step. Problems test your knowledge of mathematics in depth. All of it. Oh, by the way, I had that box. Have the references in here? Yeah, prospect.
This is only one trial. Thank you. I can't prove everything.
think it says Freeman. I think so. I can't even. John? Jeremy, that one? Ben? Here. Mar. More Ben. Let's take a look at this problem together. Then we have one more concept to cover and this lesson is over. So we are going to apply the same principle where we get rid of the exponent by applying ln to both sides. So we first make both sides. You say y equals limit x goes to infinity 1 plus 1 over x raised to ln x. And then I'm going to use ln on both sides. Get ln y is equal to first limit x goes to infinity, drop down ln x, and then have another ln 1 plus 1 over x. And now this is infinity and this is 0. We use 1 over f. So ln y is equal to. Now, how about I just remind you of something, and then you might want to keep note of that. Don't worry about it. We'll figure out something else. So we have multiplication of these two. We have the limit x goes to infinity, ln of 1 plus 1 over x divided by ln x. Sorry, 1 over ln x. Much better. So what do I have? I have 0 over 0. Very good. Which means that I can unleash L'Hopital's rule. Don't forget the limit. -5 per line. So 1 plus 1 over x and its derivative on top 1 over x squared, and on the bottom here, what's the derivative? It's ln x to the negative 1, which means negative 1 times the derivative of the inside, sorry, negative 1, and then ln x to the negative 2 times 1 over x in front. So it's negative 1 divided by x ln squared x. This is how awesome this stuff is. So what I can do is, again, multiply two that are far apart, multiply two that are close by. So solving a double fraction, ln y is equal to, now we're just working on algebra for the rest of the problem. Limit x goes to infinity. Two that are close by, x and x squared, they cancel, so you get minus ln squared x divided by x divided by negative and negative will cancel actually, so I don't need negatives. I have 1 plus 1 over x here. So now we multiply by x both of these. Ln y is equal to the limit x goes to infinity, and then I have ln squared x over x plus 1. And now you try to use the infinity, you get infinity over infinity, which means L'Hopital again. So ln y, we don't know that we did L'Hopital's rule there. The derivative of this is 2 ln x times 1 over x divided by 1. So if you rewrite this carefully, you get 2 ln x over x. Apply infinity over infinity, L'Hopital again. Yes.
Oh, wait. Okay, now what's happening?
Is there a problem?
Okay, well, it stopped, went backwards, and now it's catching up.
Awesome. 2 over x divided by 1. Finally, we're getting 0. So ln y is equal to 0. Let me try to do one of these right. Y is equal to 1. Therefore, original problem, limit x goes to infinity of 1 plus 1 over x raised to the ln x is equal to 1. Wow.
Just a bit.
Yes. Problems are a little bit lengthy with lots of ST algebra, right? But nothing that, you know, an hour and a morning coffee can't solve. That's tomorrow morning, Sunday. Yes.
Well, the first time you did the 1 over x, is there any particular reason you chose ln of x versus ln of 1 plus 1 over x?
It's easier. It goes in denominator as 1 over. So if you chose this one, it will be ln x over 1 over ln 1 plus 1 over x. And then you just have to worry, it's not, then you are making yourself double chain rule there.
Yeah, that's the way that it's.
You try to pick easier function to go down because it's going to get 1 over that function, which makes the derivative worse. But then it's, you know, it was like the last elections. You pick a lesser evil. That was long. The last part of this 2-hour-long lecture with a 7-minute break is the growth rate of functions. Growth rate of functions in the sense that when you have certain functions divide each other, if they are not of the kind, and you send limit to infinity, you can make a conclusion about the answer for that limit just because you know how quickly functions grow. And then we're going to see that if you have a fast-growing function divided by a slower-growing function, the limit is going to be infinity. If you have slow over fast, it's going to be 0. If they are the same order, then it could be anything, but most likely will be coefficients and so on. So there's another part. This is still taking limits. The growth rate of functions is given in a textbook. I will write it here. So start as far left as you can in your notebook. So ln raised to any power of x is going to be slower than polynomials. It's going to be slower than when you multiply the polynomial with the ln. It's going to be slower than multiplying two polynomials. It's going to be slower than exponential functions. It's going to be slower than the x to the x, which is a boss. Growth rate of functions. Now let's see what does this mean. I'm going to pick a few of these, compute some numbers. So I'm just going to have x, 2x, x squared, 2 to the x, and x to the x. I'll pick 1, 2, 3, 4, 5 as values. So if I'm doubling these, I get 2, 4, 6, 8, 10. So clearly 2x grows faster than x, right? Because every number is twice as large. Now how about x squared? Well, 1 squared is 1, and 2 squared is 4. So you see how it kind of struggles to beat 2x. But then you have 3 squared is 9, and that beats 6. And then 16 beats 8, and then 25 beats 10. So definitely x squared beats the linear, right, in terms of the growth. It kind of started rocky, right? Not that great. But then it caught up, and then it just, right. 2 to the x. So 2 to the 1 is 2. And 2 squared is 4. It's keeping up. 2 cubed is 8. You see, it's kind of losing to x squared. And then it goes 16, catching up. 32. You know what? I should probably add 6. Because that one would really show how exponential takes off. Right? So it's kind of struggling to keep up with x squared. And then right after the 4, look at that, 25, 32, and then 36, 64. And then x to the x is just blows everything out of water. You have 1 to the 1 is 1, 2 squared is 4, 3 cubed is 27, 4 to the 4, that's 16, yeah, 256. 256 on the 4th entry, look at that. And then 5 to the 5. So you have, that's 25 squared is 625 times 5. So 3125, if I did this right. Is it? 3125? Yes. And what's 6 to the 6? Using your trusty Apple garbage. Hey. And we have the winner, right? All right. So we are getting the sense of what I have up there in red looking at this chart. And you can also get this if you look at the graphs, because these are all y values. If you think about ln graphs, they graph like this, and then the linear graphs like that, and then the quadratic graph goes like this. And you can see that if you are to strike a line here, you see that the log has the smallest value, then the linear, then the quadratic. If you draw exponential function, it'll go even crazier, right? So you can see, right, this is ln x, this is x squared, this is, let's say, e to the x, or 2 to the x, whatever. So you can see how y values for the same x, let's say x is equal to 2 in this case, you can see how they line up. So now, what good is this? First of all, what I'm going to write here is not mathematical notation. It is our way of thinking to say that the limit x goes to infinity over slow or fast is going to be 0. I have to put this in quotation marks because this is not mathematical notation at all. This is just the way we quickly think about things. X goes to infinity of fast over slow is infinity. So I can solve these problems extremely quickly. If I say limit x goes to infinity and I put x to 1000 plus 3 divided by, let's say, e to the x. I don't have to think about this. I don't care that the exponent is 1000 on x. E to the x is eventually much faster growing function, eventually. So I understand x to 1000. Yes, that is insane growth. But you know what? E to the x is eventually going to beat it. That's why you had this kind of symbol. You know, just wait long enough, right? Patience, young Padawan, right? That's the wise words. So this is immediately 0. Immediately, without doing any work, just because polynomials will always grow slower than the exponential, which means you have the larger value in denominator, 0. Another crazy example would be, let's say you have x to the x divided by 300 times 10,000x plus 7, let's say. All right. So looking at this thing, and you say, wow, well, 300 to the 1 is 300. 300 to the 2 is going to be what? 90,000, right? That grows extremely fast. But look, it's the boss up there, right? So infinity, without any calculations, because you have the faster, eventually faster growing function, right? It's a faster growing function, so it will eventually beat whatever we put down there. So you have to understand that numbers that you use as coefficients and constants, they don't mean and contribute to this procedure at all. It is the type of the function. You need to memorize that the log is sluggish, and then polynomials, and then exponentials, and then x to the x. You're memorizing that sequence. And the numbers that are used are not important at all, because if you went sufficiently long, the one that is faster growing will beat it eventually. And that is the end of 4.7. L'Hopital's rule and growth of functions. Stream out. We'll be back after the break with 4.9 anti